China just created a material harder than diamond that costs 1/10 the price to produce. You heard that right, 1/10. That is the difference between a Ferrari and a used Honda Civic sitting in the same parking lot doing the same job. And that is just the beginning. If that already sounds like something you need to understand before everyone else does, hit a quick like and subscribe so you don't miss the next one. By the end of this video, you are going to understand exactly why this material doesn't just compete with diamond. It threatens to make diamond industrially obsolete. Here is where the story really begins, with a problem in precision manufacturing that nobody outside the factory floor has ever bothered to explain to you. Think about your kitchen knife. You sharpen it on a whetstone, and after a few strokes it cuts clean again. Now imagine trying to cut something harder than the whetstone itself. That is the problem. Industrial manufacturing has been quietly losing sleep over for decades, and it is the reason this story matters as much as it does. Diamond sits at the top of the hardness scale, 10 out of 10 on the Mohs scale, which is the chart every geology student memorizes in their first week. Nothing found in nature scratches it. Nothing cuts it except itself. And for over a century, industry treated diamond as the ultimate cutting tool, the thing you reach for when everything else fails. But here is what most people never think about. Diamond has a weakness so fundamental it changes everything about how you can use it. Put diamond under high heat and it starts to degrade. Expose it to iron-based metals, which is most of what the world's factories are cutting, and a chemical reaction begins that eats the diamond surface alive. A material that nothing in nature can scratch gets quietly dissolved by the metal it is supposed to be cutting. That is not a minor footnote. That is a structural flaw at the center of the entire precision manufacturing industry. So what does industry do? It works around it. Factories run diamond tools at lower speeds to manage heat. They swap tools more frequently. They avoid certain materials entirely. They build entire production workflows around the limitations of a material they have no alternative for. The cost of that compromise is built into the price of every precision-made object you have ever bought, every engine block, every turbine blade, every smartphone chassis. Now, here is the forced reframe that puts this in perspective. The global cutting tools market, the drills, the blades, the grinding wheels, the inserts that factories around the world burn through every single day, is worth over $80 billion annually. $80 billion. That is larger than the entire economy of some European nations. And a significant portion of that market exists, not because these tools are performing well, but because they wear out, break down, and get replaced constantly because no material has been good enough to last. That is the size of the problem China just aimed at. The industries that depend on precision cutting are not small players. Not just a few machine shops. You are talking automotive production lines, aerospace component manufacturing, oil and gas drill heads, medical device fabrication, and the semiconductor industry, which is arguably the most important manufacturing sector on the planet right now. Every single one of them is constrained by what their cutting tools can handle. And for most of the 20th century, the honest answer to the question of what is the best cutting material available was diamond, with all its heat sensitivity, all its chemical reactivity, and all its cost attached. The world built its industrial base on a material with known, documented, irreducible flaws because nothing better existed. Until now. But understanding why China's new material is different requires understanding something about atoms that most people were never taught, and that is where this story gets genuinely extraordinary. Picture a standard ice cube tray. Every cube sits in its own slot, perfectly arranged, perfectly spaced, perfectly repeating. That is roughly what a crystal looks like at the atomic level, atoms locked into a pattern that repeats in every direction with mathematical precision. The pattern determines everything. The same atoms arranged differently produce completely different materials with completely different properties. Carbon atoms arranged one way give you graphite, the soft gray material inside your pencil. Rearrange those exact same carbon atoms into a different pattern, and you get diamond, the hardest natural substance on Earth. Same element, completely different arrangement, completely different reality. Now, take boron and nitrogen, two elements sitting right next to carbon on the periodic table. Arrange them, in a flat, layered structure, and you get hexagonal boron nitride. It is slippery, soft, and used as a lubricant. But force those same atoms into a three-dimensional interlocking structure, the kind that only forms under enormous pressure and heat, and something extraordinary happens. You get cubic boron nitride, a material so hard it sits just below diamond on every hardness scale ever devised. And unlike diamond, it does not react with iron. It does not degrade under high heat the way diamond does. It cuts the materials diamond cannot touch. Researchers have known this since the 1950s. General Electric synthesized cubic boron nitride in 1957, the same decade they cracked artificial diamond synthesis. The Western industrial world understood what this material could do for over half a century, and for most of that time, producing it in meaningful quantities at viable cost remained just out of reach. Here is what most people get wrong about material science breakthroughs. The discovery is rarely the hard part. Turning a laboratory result into an industrial process, one that runs reliably, at scale, day after day, producing consistent output, that is where most breakthroughs go to die. You can know something works in a lab for 50 years and still not have a factory-ready process for it. China's achievement is not that they discovered a new hard material. It is that they solved the manufacturing problem that the rest of the world spent 50 years failing to crack at scale. They built the industrial infrastructure, the high-pressure synthesis chambers, the quality control systems, the raw material pipelines to produce ultra-hard boron nitride compounds at volumes and price points that change the economics of the entire industry. And they did not do this overnight. China's investment in high-pressure materials research stretches back to the 1980s. State-backed laboratories spent decades running experiments, building prototypes, failing, iterating, and scaling. By the time the rest of the world started paying attention, China had already built a manufacturing base that competitors would need a decade and billions of dollars to replicate. The timeline matters here. This was not a sudden sprint. It was a 40-year marathon run, quietly, deliberately, and almost entirely out of the spotlight of Western technology coverage. While the semiconductor race and the electric vehicle race were dominating headlines, a parallel race in materials science was being run and won, with almost no public attention at all. Here is the detail that puts everything into perspective. China now accounts for the majority of the world's synthetic superhard material production. The country that spent decades importing precision tooling technology has positioned itself as the dominant supplier of the material that makes precision tooling possible in the first place. That inversion did not happen by accident. But knowing what was built and why it took so long is only half of the picture. The other half, the part that will genuinely change how you think about manufacturing, is understanding the machine that makes all of this possible. And nothing about that machine is small. Squeeze a walnut in your fist as hard as you can. You feel the resistance. Now imagine a machine that generates pressure 1 million times greater than anything your hand could produce. Pressure so extreme, it recreates conditions found 30 miles below the Earth's surface inside a chamber you could walk around in about 30 seconds. That is what a large-volume, high-pressure synthesis press looks like, and it is the reason most countries never scaled this technology. Building one is extraordinarily difficult. Operating a facility full of them is another challenge entirely. The numbers involved in these machines reframe what the word pressure even means. Superhard material synthesis requires pressures between 5 and 20 gigapascals. 1 gigapascal is roughly 10,000 times the pressure of the atmosphere you are sitting in right now. 10,000 times. The pressure at the bottom of the Mariana Trench, the deepest point in any ocean on Earth, is about 1/10 of a gigapascal. You are not recreating ocean floor conditions. You are going orders of magnitude beyond them. Simultaneously, the temperature inside the chamber reaches thousands of degrees Fahrenheit. For a brief controlled window, you have recreated the interior of the planet inside an industrial building. Here is the brutal catch that stopped most Western manufacturers from scaling this process. The anvil blocks that generate the pressure wear out. The seals degrade. The consistency of the output, the crystal size, the purity, the hardness uniformity varies in ways that are incredibly difficult to control at scale. Running one of these machines reliably is hard. Running 50 of them simultaneously with consistent output quality while managing raw material, inputs, and energy consumption that is an industrial systems problem of the highest order. China solved it by doing what China does better than almost any other country right now: building at scale relentlessly and iterating faster than competitors can track. The city of Zhengzhou in Hainan province became the global center of superhard materials production. Facilities there operate hundreds of high-pressure synthesis presses simultaneously. Hainan province alone accounts for the majority of global synthetic diamond and cubic boron nitride output by volume. The combined output of those facilities dwarfs anything the rest of the world produces. And here is what makes that geography significant beyond the output numbers. Hainan sits at the center of China's industrial heartland. Raw material supply chains, energy infrastructure, and manufacturing expertise are all concentrated within a few hundred miles. The cluster effect, where suppliers, manufacturers, researchers, and engineers all operate in proximity, creates an innovation and cost efficiency loop that is nearly impossible to replicate by building a single facility somewhere else. The machine and the facility are infrastructure. What matters to the world is what comes out the other end, and what happens to global manufacturing economics when the price of the hardest cutting material on Earth drops by a factor of 10. That is where this story stops being about chemistry and starts being about power. Here is a simple way to understand what a 10-fold cost reduction does to an industry. Imagine surgeons currently perform a procedure using a tool that costs $1,000 per use. The procedure gets done when it is absolutely necessary and rationed carefully when budgets are tight. Now, cut that tool's cost to $100. Suddenly, the procedure gets performed more frequently, on more patients, in more hospitals, in more countries. The technology did not get better, it got cheaper. And cheaper changed everything about who gets access and how often it gets used. That is exactly what is happening to precision manufacturing right now. Ultra-hard cutting tools made from cubic boron nitride were previously priced out of reach for most mid-tier manufacturers. A fully tooled production line using premium superhard materials carried a cost that only high-margin industries like aerospace or premium automotive could justify. Everyone else used inferior alternatives, accepted lower precision, shorter tool life, and slower cutting speeds as the economic reality of their sector. At 1/10 the cost, that calculation inverts completely. Now here is the part that blows people's minds. The benefit of cheaper superhard tooling is not just that you spend less money on the same process, it is that you can run the process differently. Superhard tools cut faster than conventional alternatives. They last longer between replacements. They hold tighter tolerances, meaning the parts they produce are more precise with less variation. When you combine faster cutting speeds with longer tool life and tighter precision, the productivity gain compounds in ways that dwarf the raw cost saving on the tool itself. The automotive industry feels this first. Engine components, transmission parts, brake rotors, these are high-volume, tight-tolerance parts made from hard metals that conventional tooling struggles with. Chinese manufacturers equipped with affordable superhard tooling can produce these components faster, to higher precision, with lower tooling costs than competitors, using conventional alternatives. In an industry where profit margins on individual components can be measured in cents, a compounding productivity gain is the difference between winning a supply contract and losing it permanently. Aerospace is the next frontier. Titanium and nickel superalloys the materials inside jet engine components, and airframe structures are notoriously difficult to machine. They generate enormous heat during cutting and destroy conventional tooling at an alarming rate. The cost of machining these materials is a significant fraction of the total component cost. A cutting tool that handles superalloys at lower cost and higher speed does not just save money on the tool, it restructures the economics of building aircraft components from the ground up. Here is what most people never connect. The country that controls the cost of precision cutting tools controls who can afford to manufacture advanced components at scale. If your competitors can machine titanium at half the cost you can, they win aerospace contracts. Precision manufacturing is a competition fought at the level of individual microns and individual dollars per component, and Superhard tooling sits at the center of both battles simultaneously. But the industry where cheaper, Superhard materials carry the most explosive implications is not automotive. It is not aerospace. And that industry just got a new and unexpected front opened against it. Most people think of geopolitical competition in terms of missiles, trade tariffs, or diplomatic summits. The real competition, the one that determines outcomes decades from now, happens at the level of supply chains. Who makes the components? Who controls the materials? Who has the infrastructure to produce the things that everything else depends on? That is where this story lands, and it is a story almost nobody in mainstream coverage has connected yet. Diamond tooling has historically been dominated by a small number of players. Element 6, a De Beers subsidiary, became one of the world's leading synthetic diamond producers for industrial applications. Companies in the United States, Japan, South Korea, and Germany built precision tooling industries on top of that supply base. The supply chain for the world's hardest cutting tools ran through Western-aligned companies and institutions by default. China's Superhard material scale-up does not just offer a cheaper alternative to that supply chain, it offers an exit from it entirely. A Chinese manufacturer buying Superhard tooling from domestic producers has zero exposure to Western export controls, zero exposure to supply disruptions caused by geopolitical tension, and zero dependency on companies whose governments might restrict sales at any moment. That independence has a value that does not show up in the cost per tool calculation, but is arguably more important than the price saving itself. Here is the detail that engineers do not want to admit publicly. Export controls on advanced manufacturing equipment have been tightening for years. The semiconductor equipment restrictions that the United States, Netherlands, and Japan imposed beginning in 2022 were designed to slow Chinese chip manufacturing by denying access to the tools needed to build advanced fabs. The logic was sound. You cannot make chips without the right machines, and if you cannot get those machines, your chip industry stalls. But that same logic cuts in every direction. If precision cutting tools become subject to similar restrictions, or if the countries that currently dominate Superhard tooling supply decide to use that position as leverage, the impact on global manufacturing would be severe. China recognized this exposure and moved to eliminate it. The Superhard materials buildup is, among other things, a supply chain immunization program running in parallel to every other technology independence initiative China has launched over the past decade. Now here is the part that nobody is reporting. The implications run in both directions. Western manufacturers who currently source Superhard tooling from Chinese suppliers, and there are many, because Chinese pricing is already competitive, now face a different kind of exposure. China demonstrated willingness to use material export restrictions as a geopolitical tool when it restricted gallium and germanium exports in 2023. Superhard materials represent a second category of potential leverage, one that connects more directly to manufacturing output than almost anything else on the list. The countries paying attention to this are beginning to understand something important. And understanding it requires going one layer deeper into the specific industries where this material does not just reduce costs, but removes a ceiling that has been holding entire sectors back for years. Run your finger along the edge of a knife blade that has just been sharpened on the finest stone available. You can feel the edge, a line so thin it barely exists in 3 dimensions. Now imagine needing that level of precision not on a kitchen knife, but on a silicon carbide wafer 1 millimeter thick, being sliced into hundreds of individual chips, each containing billions of transistors spaced just a few atoms apart. The tool doing that cutting cannot flex, cannot heat up, cannot wear unevenly. It has to perform the same cut, to the same tolerance, 10,000 times in a row, without variation. That is the semiconductor dicing problem. And it is one of dozens of precision cutting challenges where Superhard materials are about to rewrite the rules. Silicon carbide is becoming critical for electric vehicle power electronics. It is almost as hard as diamond itself. Cutting it reliably, at speed, without introducing microcracks that destroy the electrical properties of the finished wafer, requires cutting tools that push the boundaries of what materials science can deliver. Cheaper, more capable Superhard tools do not just reduce cost in this process, they improve yield. And in semiconductor manufacturing, yield improvement translates directly into dramatically lower cost per functional chip. That is not an incremental gain. That is a restructuring of the entire economics of advanced power electronics. If that connection between a cutting tool and a power chip surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. Move to medical devices. Surgical instruments, orthopedic implants, and dental tools require machining tolerances measured in microns millionths of an inch. The materials involve titanium alloys for implants, cobalt chrome for joint replacements, are the same superalloys that defeat conventional cutting tools in aerospace applications. Every orthopedic implant manufacturer in the world is fighting the same battle. How do you machine biocompatible hard metals to surgical tolerances at a cost that does not make the final device prohibitively expensive? Affordable Superhard tooling is a direct answer to that question. It is also a supply chain question, and the country that dominates Superhard tool supply shapes who can manufacture medical devices competitively at global scale. Now here is what makes this incredibly exciting when you zoom out across all of these sectors simultaneously. The impact of cheaper, Superhard materials is not linear. It does not flow evenly across all applications at the same rate. It concentrates in the sectors where hard material cutting is the binding constraint, where the limitation on what you can build, or how fast you can build it, is defined by what your cutting tools can handle. In those sectors, a step change in tool capability and cost does not produce incremental improvement. It removes a ceiling. And across semiconductors, medical devices, aerospace, and energy technology simultaneously, that ceiling just moved. But there is one final dimension to this story that turns a materials breakthrough into something that future historians might point to as a genuine inflection point, and it requires going all the way to the top of the picture. There is a pattern in the history of industrial civilization that repeats so reliably, it almost qualifies as a law. Whoever controls the material that makes everything else possible controls the era. Britain controlled coal and steel in the 19th century and built an empire on it. The United States controlled oil refining and later semiconductor design in the 20th century and defined the global order around those advantages. Every era of industrial dominance has been built on a foundation, material, something so fundamental to the production of everything else that controlling it means controlling the productive capacity of the civilization itself. For most of the 20th century, that foundation material for precision manufacturing was industrial diamond. The supply chains for it ran predominantly through Western-aligned producers. That alignment was not incidental. It was a structural feature of the post-war industrial order that reinforced Western manufacturing advantages in aerospace, defense, and advanced electronics for decades. Here is what most people never connect about what China just did. The Superhard materials buildup is not happening in isolation. It is one move in a much larger strategic sequence that includes rare earth processing dominance, silicon carbide wafer production capacity, gallium and germanium export controls, and now the material science layer that sits underneath precision manufacturing itself. Each individual move looks like an industrial policy decision. Together, they look like a deliberate effort to control the material foundations of the next industrial era. The countries that are paying attention understand that the competition for technological leadership in the 21st century will not be decided primarily by who writes the best software. It will be decided by who can manufacture at scale, at cost, and without dependency on adversarial supply chains. Materials science is the layer below all of it. It is the thing that makes the thing that makes the thing. China's super diamond is 10 times cheaper than the real thing and harder than almost anything else on Earth. It does not compete with natural diamond in the industrial tooling market. It replaces it. Not gradually, not partially, category by category, application by application, it removes the economic justification for using anything else. The world built precision manufacturing on the assumption that the hardest cutting materials would always be expensive and would always flow through supply chains that certain countries controlled. That assumption is now wrong. One country changed it. And the industries, the supply chains, and the geopolitical arrangements built on top of that old assumption are going to have to reckon with a new reality whether they are ready for it or not. If this changed how you think about materials, science, and geopolitical competition, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think Western manufacturers will move fast enough to build independent super-hard material supply chains? Or has China already locked in an advantage that is simply too large to close?